my screen okay? Where it has, I'm writing M and T. We want a best fit line. So remember, in doing best fit lines, we're trying to linearize our data, and the function we're going to use now, during the year, we talked about 2 different ways to get a linear fit or get a best fit line or linearize your data. One of them is to try and make your function look like this. One is to solve for the unknown variable to which they want the slope, which would be solving for k. So I can do this either way, but let me be clear. Some ways are easier than others. In this particular example, it's going to be messy. Neither of them are particularly easy. So remember, the goal here is to put together the things that you are graphing so that one of them lines up with y and one of them lines up with x. So that's what we're going to try and do. And we have m for the mass and t for the period. Those are the 2 things that we have. So since it's already solved for period, I'm going to write my function y equals mx plus b right above that, and recognize right at the beginning that b has got to be 0. So I'm not going to have a value for b, so I'm going to ignore that. And now I'm going to focus on what's left. The m here is the constant that represents the slope. X represents one of the variables and y represents one of the variables. So what I want to do is I want to take everything that's in this really confusing looking term and maybe break it up into pieces. I'm just breaking it up into the pieces that are there. This is a clear constant. This is something I measured, and this is what I am looking for. That okay? So remember, I want to get the thing that I have measured lined up with x and lined up with y. So I'm going to change the order here. I've changed the order. We okay? Now by changing the order, I have something here that can be plotted on the y-axis, something here that can be plotted on the x-axis, and something here that is supposed to be a constant. So, indicate below which quantities could be graphed to determine the spring constant K of the spring by using a best fit line. It looks to me like I want to plot period on the y-axis and square root of mass on the x-axis. I could do the reverse of that too. It doesn't matter as long as it's period versus square root of m. Which means, of course, you have to take 0.3, 0.6, 0.9, and 1.2 and find their square root. Now, they want you to actually go the extra mile and do all that, graph it, which I would like you to do too, even though I'm not sure they're going to do this on the exam. But they could. They did one, you know, out of 5 years, they've done one like this. So now I would put, you know, the square root of m here and period here. This should give you a graph that is a straight line. Should, being the operative word. So slap your ruler down, find a straight line, and you're not done yet because this is where it actually gets kind of hard. When you find that slope, that is not K. that slope will be 2 pi times the square root of 1 over k. So now you have to solve that for k. I see your hand go up. Go ahead. Yep. That works. That's right. And I was going to talk about that part too. So to me, this seems more complicated, but this works for every case, especially cases where you have an inverse relationship. You can't do the other method if you have an inverse relationship. But in this particular case, because period equals 2 pi times the square root of m over k, we could solve this for k and see if it puts the things that are measurable on opposite sides of the fraction. So I'm going to first divide both sides by 2 pi. I'm going to square both sides. And I'm going to cross multiply to solve for k. Now, if you use this method, in this method, I'm going to plot this on the y-axis and this on the x-axis. So period squared here and 4 pi squared m here. This should also be a straight line, but the difference, and perhaps the advantage, is that this straight line will give you a slope that just equals k. So those are the two methods we talked about in class. Look, I think for this one, this second method is much easier. But like I said, there are times when we can't do this one. If both of your variables end up in the numerator or the denominator, you can't graph it and get the slope. So we need to be aware that there's two methods to linearize. That doesn't always mean that one is going to be, successful. All right. Does that answer your question? This one's tough. I know this one's a hard one. Any of these ones that have you do all this kind of work is pretty hard. All right. It is 2 minutes until this thing's going to shut down on me. But is there another question you guys would like me to take a look at? I could at least get it started. And I'll keep a running session from the other classes too, so that if we ask other questions in other classes, we have their answers as well. Again, what we're looking to do is, if this is our function for acceleration, we know there's a velocity and a period function that are going to be similar to this because we've seen them now. So all I have to worry about is this part that's inside the sine portion. And I know that it's going to give me a repeating function every time it advances by 2 pi. So I just assume that in the first period, from 0 to t, we're advancing by 2 pi. So I just plug in capital T to represent period, and I set whatever else I have in there equal to 2 pi, which means the period is going to be 2 pi divided by omega. Okay, Rachel? I think one of those answers is there. Yep, question, it's D. 2 pi over omega. Well, guys, believe it or not, that is the end of class. I'm sure you're not terribly disappointed by that, but you might be a little bit disappointed. I know that I will be sad that I will not get to see any of you until tomorrow. Well, that was abrupt. Well, for everybody in 6th period who was paying attention to this problem, and for the the group of people who weren't paying attention but had their little boxes on the screen, let me just be really clear. I forgot to hit the record button when going over this question, so I'm going to redo it, even though all of the answers more or less appear here, and I'll be a little bit more explicit. All right, Avery. And I'm saying Avery because Avery was the one who asked, and we ran out of time. So I broke out the big guns, got my good microphone. Yes, the good microphone. It makes me feel like a rock star whenever I use it, and it's like all cool, and it's like pointed at me, and it's in stereo, so you can hear me on this side, and then maybe you can hear me on this side, and then maybe you can hear me on this side. It's like I'm moving in stereo, so it's kind of cool. I like to have it, blah, blah, blah. So we're looking at question number 1, and question number 1 was about the 20 kilogram box, and just a couple of points about this one. We could have done this problem, or a lot of this problem, first semester, because it's arguably it's a conservation of mechanical energy question. But I kind of like it because it has some good stuff from first semester that I'm hoping you all kind of remember a little bit, but maybe not so much. So we've got this 20 kilogram box, but over here in the corner, waiting for it patiently, is a spring of unknown spring constant. Because it's not like when you go to the spring store, they put the spring constants right on the springs. At least not any of the spring stores I've gone to. They say the box is traveling at 4 meters per second and is going to contact the spring. And when it does contact the spring, it's going to compress the spring. And I would love to just cut and paste this, but that on this app never works out the way I want it to. So I'm going to, waste your time and mine redrawing it. So technically I'm such a liar, so I just paused it and drew them there so that it looked like, boom, it was just there, and there it is. So 4 meters per second. The first question actually asks something that I think is incredibly important first semester topic, and it definitely plays a role in here too. It says the spring does work on the box from the moment the box first hits the spring to the moment the spring first reaches its maximum compression. Indicate whether the work done is positive, negative, or zero. I love this question because there is work done on the spring by the box, and there's work done on the box by the spring. So, which is which? And which one's positive, which one's negative? Well, the work done by the spring is done on the box. The spring applies a force to the box. So, because of that, the force of the spring on the box does work on the box by the spring. So in trying to answer that question, I can consider that we can calculate the work just by knowing what the change in kinetic energy is of the box. So since the box is brought to rest and we know its initial speed is, we can say that the work done on the box is equal to 0 minus 1/2 mv squared, or looks like negative 160 joules of energy. This will be the work done on the box by the spring. There's an equal amount of work done on the spring by the box. But the next question is calculate the spring constant of the spring. Well, all of that energy goes into compressing the spring here. And this is where we get the elastic energy stored in the spring. We know that the spring was compressed a total distance of 0.5 meters. So I can state pretty clearly that there's 160 joules of energy stored in the spring when it is compressed 0.5 meters. When I square that, of course, you get 0.25, and half of 0.25 is 0.125 K equals 160. And from there, we can get K. All right, so that's going to be a value of 1,280 newtons per meter. So again, this is looks like question A, and of course it's negative. Question B gives us spring constant. Question C, calculate the magnitude of the maximum acceleration of the box. The maximum acceleration of the box occurs when it's at its maximum displacement, which is here again. And that maximum acceleration comes from looking at the fact that the net force equals kx and setting that equal to ma. So here the maximum acceleration is going to be k over m times x. Now, I know I moved the negative sign. Negatives for direction. And they're not really interested in the direction in this problem. I could leave the negative there if you'd like, but at this moment you should be able to say instead that when the spring is compressed, the force will be to the right based on my drawing. Either way, this is still going to be 1280 divided by the mass of 20 times displacement of 0.5. Which gives us an acceleration of 32 meters per second squared. All right, so question D, calculate the frequency of oscillation of the box. All right, this is probably the last bit I can put on this page before I'm going to run out of space, but the frequency of oscillation is just a plug-and-chug formula, 1 over 2 pi times the square root of k over m. So it's not particularly exciting, but still this is what we have to do. This is going to be 1 over 6.28 times k is 1280 divided by 20, 64, square root of 64 is 8. So we'll get 8 divided by 6.28, which is 1.27 hertz. Now going on, it says, let x equals 0 be the point where the box makes contact with the spring with positive x directed to the right. All right, positive x is directed to the right. On the axis below, sketch the kinetic energy of the oscillating box as a function of position for the range x equals 0.5 to x equals positive 0.5. And that's an interesting question. And by interesting, I mean kind of a bit of a pain. I'm going to have to click this out a bit. So for the last part, we have to do a graph, and it says on the axis below, sketch the kinetic energy K of the oscillating box as a function of position. Now, that's very, very careful. It's a function of position, so this is not a sine wave. It's saying how much kinetic energy does it have based on where it is. Now, we know the box is oscillating back and forth between 0.5 and negative 0.5. And so, yeah, we know what the energy is. The max energy it can have is 160 joules. So the thing is, when the box is at 0.5, it stopped. So we know it has no kinetic energy there. And when it's at negative 0.5, it is also stopped. So it can have no kinetic energy there. And we know it has maximum kinetic energy, 160 joules, when it's at equilibrium. That was right when it contacted the spring. Now the real question is, how do I connect these together? Well, I'll remember that the velocity is equal to the square root of k over m a. Oh wait, what am I doing? What am I doing? I don't want to do that. I don't want to do that at all. I want to remember that the system is oscillating between these two, and that kinetic energy is 1/2 mv squared. It's got a squared relationship here. So I know that the energy is going at the same time that it's going from, ooh, that looked pretty bad. Let's try it again, maybe a little slower. It's going from 0 to kinetic at the same time the potential is doing the opposite. So I'm kind of expecting that I have kind of a curve like this as the energy leaves the kinetic and becomes potential. In fact, I think the potential probably looks like the opposite of this. Potential probably looks like this. Now, at the same time, they asked about the acceleration as a function of position. This one's probably going to frustrate some of you. I mean, I don't know why, but it probably will. The acceleration as a function of position between 0.5 and negative 0.5. Net force equals minus kx. It's only the one force acting. Ma equals minus kx. So A equals minus k over m times x. I'm graphing A on the y-axis and x on the x-axis. I should have a straight line with a negative slope. And the negative slope is k over m. So I'm pretty confident that there it is. That's got to be it. It's a straight line with a negative slope. So, pretty straightforward. That's what I was looking for. The kinetic energy one might have been a little bit tricky, but I don't think the other one is. So I'll post this and